Hi everyone, this is Mrs. J, and today we're going to be graphing exponential and logarithmic functions with transformations. But first, please pause the video and give the warm-up a try. All right, go ahead and check your work here. You'll notice that I picked very strategic x values. They might look weird at first, but if you look at what we're plugging into, if I have a base 2 logarithm, I'm going to pick x values that are powers of 2, so 1/4, 1/2, and then I'm always going to pick 1 for these functions. You'll notice I picked the same x values when my base is 1/2. These are simply just powers of 1/2. And you'll notice that the y values are simply flipped. So your f of x function ends up looking like this, g of x looks like this, and they both have the same domain and range. They will never quite touch 0. You'll see they get really close to x equals 0, but will never quite touch it. So these graphs actually have asymptotes, just like our exponential function. But this time, these asymptotes are vertical. So the parent functions have vertical asymptotes at x equals 0. Their range, these will go up and down forever. They're both all real numbers. And you'll notice when your base is larger than 1, you have that increasing graph for the parent function. And when your base is between 0 and 1, you have that decreasing graph. And then just a quick reminder, just by definition for logarithmic functions, the base can be any positive number except 1. So the base cannot be negative, the base cannot be 0, and the base cannot be 1. So here's just an overview of the parent functions for log base b of x. So you can see log base b of x is right here. This is for when b is greater than 1. So we have that increasing graph. And here's log base b of x in red when b is between 0 and 1. And you'll notice that in these examples we have their inverse functions plotted. So remember, logarithmic and exponential functions are inverses. So this is what b to the x looks like when b is greater than 1. And you'll notice that if you take those points and reflect them over that line y equals x, you get the graph of your logarithmic function. Same thing for when b is less than 1. Here's what that graph looks like for exponential, reflected over the line y equals x, and you get your logarithmic function. So that is one of the definitions of an inverse function, is that they are reflected over this line y equals x. You also notice that you can take the x and y values and literally swap them to get any inverse function. And you would also do the same with the domain and range. You would literally swap the domain and range. So first we're going to graph exponential functions, and we're going to do this with transformations. We looked at the parent functions of these graphs 2 lessons ago, but now we're going to start to transform them. So these are the same rules that we've used with every type of function we've learned so far this year. We have horizontal translations, so when you add or subtract specifically to or from x. So remember, subtracting from x actually moves your function right. Adding to x moves it to the left. Then we have our vertical translation, and this is where you add or subtract from the entire function. So you can see if we add to our function, we go up. If we subtract, we go down. We had 2 types of reflections. If you multiply the x specifically, it reflects over the y-axis. And if you multiply the entire function, it reflects over the x-axis. And then we had our horizontal stretches or shrinks. These were the tricky ones because it has that reciprocal factor. So if you see an a value, the factor is actually 1 over a. So here, this would actually be, even though it's multiplied by 2, we see that's a shrink by 1/2. And here, this is like saying 1/2 x, so we're dividing by 2. This is actually stretched by a factor of 2. And last, we have that vertical stretch or shrink, so when we're multiplying out front. And for this one, whatever you see is the factor. So here we're multiplying by 3, so we have a stretch by 3. Here we're multiplying by 1/4, so we have a shrink by 1/4. So again, it's important to note where you're doing these things. Are you doing it specifically to x or to the entire function? And then it's also important that you're able to determine what type of transformation it is. All right, let's give this one a try together. So first, let's complete the values for our parent function, 2 to the power of x. So here we'd have 2 to the power of negative 2, which is 1/4. Remember, a negative exponent does not make your answer negative. It causes a reciprocal action. And then we'd have 1/2. Anything to the power of 0 is 1, and then 2, and then 4. You don't have to always graph the parent function, but since this is the first one that we're doing today, maybe we can plot it just to see to remind us what it looks like. So here's what our parent function looks like. And we have another really important feature to our parent function, which was a horizontal asymptote. So these functions do have horizontal asymptotes, and for the parent function, it is at y = 0. So I'm going to add it in there because that can also transform along with the rest of my function. Now let's see if we can describe the transformations and then make our rules to transform the coordinates. So the first transformation I see is this negative out front. Since I'm multiplying the entire function, not specifically the x, this is going to be a vertical reflection, which causes a reflection over the x-axis. If you reflect something over the x-axis, you go up, down, or down, up, so that's a vertical transformation. The other change that I see is this +4, so that's going to be a vertical translation up 4 units. So let's write our rules. You'll notice here that there's nothing affecting our x value. There's no horizontal transformations. So all of our x values are actually going to stay the same. But there are two vertical transformations, the reflection and the translation. So I'm going to multiply all of the y values by -1 and then add 4 to transform them. And again, I'm pulling my parent function coordinates, and I'm going to multiply by -1. So for this first one, I'd get -1/4, and then I can add 16/4, and I get 15/4. Here, I would get -1/2 plus 8/2 would be 7/2. Here, I would get -1 plus 4, which is 3. Here, I would get -2 plus 4, which is 2. And here I get -4 plus 4, which is 0. So let's plot these points. So we have -2, 15/4, so right under 4. And then we have -1, 7/2, so 3.5, 0, 3, 1, 2, and 2, 0. Now there is something else that's going to change, and that would be our our horizontal asymptote. So anytime you have a horizontal asymptote, it will change according to the rules that affect your y value. So you would multiply your asymptote by the -1. That's not going to change my asymptote equation. But when I go to add 4, it does change the equation. So my asymptote is now going to be at y = 4. So it shifts up along with the rest of the graph. And then when we go to connect the dots, remember you will approach the asymptote, but you'll never quite reach it. So your graph looks like this. So you can see that it has clearly been reflected, shifted up, and again, the asymptote has also been shifted up. For this, our domain is always going to be all real numbers, but we do have a restricted range. The minimum value would be -infinity. The maximum value would be 4, but it is not inclusive because we never will quite reach the asymptote. And our asymptote equation is y = 4. All right, let's try another one together. Let's start with our parent function, which this time is 1/3 to the power of x. So if I do 1/3 to the power of -2, it causes a reciprocal. So it's like saying 3 squared. So that's 9, and then 3, 1, 1/3, 1/9. And then for my rules, I can see that we have a vertical stretch by a factor of 2. And that's that 2 out front. Notice that it's 2 times my base. And I'm not going to multiply those together because my base is being raised to this exponent. The base is simply part of the parent function, so that's not changing, and that would not be any type of transformation. Next thing I see is that I am adding 6 specifically to x, which is actually going to cause a horizontal translation. It will shift my graph, but remember, it goes in the opposite direction. So this will actually go to the left 6. And then last, I have this -1, so I'm subtracting to my entire function, so it's a vertical translation. It's going to go down 1. So if I write in those rules, actually first let's see what our parent function looks like, and then we'll transform those coordinates. So we have -2, 9, -1, 3, 0, 1, 1, 1/3, 2, 1/9, so it gets pretty small pretty quickly. So it does something like this. Again, this is my parent function, and we know that there is a horizontal asymptote at y = 0. So to transform my coordinates, I do have a horizontal change this time. If I want to shift a coordinate to the left, I need to subtract 6 from it. So this will become -8, -7, -6, -5, and -4. Again, I'm taking the x values from my parent function, and I'm subtracting 6, which should shift it to the left 6. Now there are 2 vertical changes here. We have the stretch, so we'll do 2 times the y values from my parent function, and then we will shift it down 1 by subtracting 1. So here we have 9 times 2, which is 18, -1 is 17. Here we have 3 times 2, which is 6, -1, which is 5. 1 times 2 is 2, -1 is 1. And then we have 2 times 1/3, so 2/3 minus 3/3 is -1/3. And then here we would have 2/9 minus 9/9 gives us -7/9. And then something else is going to shift down as well. We do have that vertical shift, so my asymptote will also shift down 1. So whatever rules apply to this, you would double the equation. That's not going to change because it's 0. So 0 times 2 is 0, but the -1 will shift it down. So maybe I'll actually sketch that in first this time. So it looks like this. And let's plot our values. So -8, 17 goes way off our graph. I'll just leave that one out. -7, 5 we can plot. And then we have -6, 1, -5, -1/3, and -4, -7/9. So still should be above the asymptote, but very close to it. And then our graph will just kind of travel along like this. So here's f of x. So again, our domain for these should always be all real numbers, but our range will be restricted. Our low value is -1, not inclusive, and it will go up forever, so our high value is infinity. And our asymptote equation is y = -1. All right, go ahead and pause the video and give this one a try, noting that this time the parent function is 3 to the power of x. Go ahead and check your work here. So we do have a horizontal translation right 2 and a vertical translation up 1. So you can see my rules here. I'm going to add 2 to the x values, add 1 to the y values, and add 1 to my horizontal asymptote equation. That will shift up along with the rest of the graph. So check your coordinates, and please check your domain, range, and asymptote equation. All right, so now we're going to move on to graphing logarithmic functions with the same process. So this should feel super repetitive at this point. This time, the way you identify if something is horizontal or vertical is if, again, it's clearly grouped with x inside the logarithm, it's going to be horizontal. And notice here, if there's no parentheses grouping it within the logarithm, then it's considered vertical. So inside, outside, these are both inside, these are both outside. But it's the same transformation rules that we've used over and over. The main thing that will be different is what our parent function looks like. Okay, so let's give this one a try together. For this one, Our parent function is log base 3 of x. So look at the x values I picked. I picked powers of 3. So let's do our parent function first. If I do log base 3 of 1/9, it's saying 3 to what power equals 1/9? How do I turn a 3 into this? The exponent should be -2. How do I turn 3 into 1/3? With -1. And then anything to the power of 0 is 1. And then how do I turn a 3 into a 3? Well, the exponent should be 1. How do you turn a 3 into a 9? You square it. So there's my parent function coordinates. And then let's look at the transformations we see in f of x. So we see this 2 out front. So this is going to be a vertical stretch by a factor of 2. And then we have a negative on the inside. So that's going to be a horizontal reflection, which goes over the y-axis. So a reflection over the y-axis. The word horizontal is optional here, but it does remind us that this should affect the x value. And then last, we see that +1. It is outside of my logarithm, which makes it vertical. So we have a vertical translation up 1. So let's make our rules. The only horizontal change we see is the reflection. So all of our x values are going to become opposite. And then for our vertical changes, we're going to multiply our y values by 2 and then add 1. So 2 times -2 is -4, plus 1 is -3. 2 times -1 is -2, plus 1 is -1. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. And 2 times 2 plus 1 is 5. Now, I also want to remind you that these graphs have another really important feature. These have vertical asymptotes. So for the parent function, it's x equals 0. So if we want to sketch out our parent function again, we can. It looks like something like this. Then we have 1, 0, 3, 1, and 9, 2. So remember, these graphs have vertical asymptotes at x equals 0. It's a vertical line, so it's x equals 0. Now, if you think about what type of things could affect a vertical asymptote, it's going to be a horizontal translation. So you're going to take whatever rules you have for your x values, you can apply them to your asymptote equation, but if you multiply this by -1, that reflection is not going to move your asymptote. So our asymptote is going to remain at x equals 0. And then if we plot our new points, it will look something like this. -1/9, -3, -1/3, -1. Again, you really just have to estimate those. And then we have -1, 1, -3, 3, and -9, 5. And now when we go to connect our dots, just remember your graph is going to get infinitely close to your vertical asymptote, but it will never quite reach it. It'll just travel along it. And I would highly, highly recommend that you always sketch in your asymptote before you connect your dots, so you kind of have more direction to your graph. And then we can see that our domain, if I go low to high, is -infinity to 0. My range is all real numbers, and my asymptote equation, again, it's a vertical asymptote, so it's x equals 0. All right, let's do another one together. This time, my parent function is log base 1/3. So you'll notice that I have powers of 1/3. So again, if you're plugging in these x values, we're going to be finding the exponents that turn 1/3 into this number. How do you turn 1/3 into 1/9? Square it. How do you turn 1/3 into 1/3? Raise it to the power of 1. How do you turn 1/3 into 1? Raise it to the power of 0. 1/3 into 3 is -1, and here we have -2. And again, we do have a vertical asymptote at x equals 0. please feel free to sketch this onto your axis if it helps you with this process. So then let's look at our transformations. Here I see a horizontal translation, and it's going to go left 7. Notice that it's grouped specifically with parentheses inside my logarithm, which is how I know it's horizontal. And then I have this -2 on the outside, meaning it will be a vertical translation, and that will go down 2. So if I want to shift my points, my coordinates, to the left 7, I'm going to subtract 7 from those x values. All right, let's try to do this with improper fractions. I have 1/3 1/9 minus 63/9. So 1 minus 63 would give us negative 62/9. Here I have 1/3 minus 21/3. So 1 minus 21 would be negative 20/3. And then I have 1 minus 7, which is negative 6, 3 minus 7, and 9 minus 7. Okay, let's look at our y value rules. If I want to translate down 2, I'm simply going to subtract 2 from my y values. So 2 minus 2 is 0, 1 minus 2 is negative 1, and then we have negative 2, negative 3, and negative 4. Now let's also think about our asymptote. I'm going to apply this same x rule to my asymptote. I'm going to subtract 7. And I see that my vertical asymptote is now at x equals negative 7. I'm going to sketch that in. So I'm going to, we want to make sure that we shift the asymptote along with the rest of the graph. All right, let's plot these points. So negative 62/9 is about negative 6.8. So we'll estimate where that is, so right around here. Then we have about negative 6.6, negative 1. We have negative 6, negative 2, negative 4, negative 3, and 2, negative 4. And then if we know that our graph is going to travel along our asymptote, I can connect my points accordingly. There we go. And it's because our base is 1/3, which is less than 1. When your base is between 0 and 1, you are going to have that decreasing graph, at least for the parent function, in comparison to when our base was bigger than 1 when we had that increasing graph. So our domain, our smallest x value that we see would be negative 7, non-inclusive. And I'll go to the right forever. Our range for these should always be all real numbers. And again, we have a vertical asymptote at x equals negative 7. All right, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your work here. So go ahead and check your parent function coordinate and asymptote. Notice that because we have that shift to the right 2, our vertical asymptote was also shifted to the right 2. So it should be at x equals 2. Check your transformation rules and your graph, as well as your domain and range. And I know here our base is greater than 1, so maybe you're wondering, well, why do I have a decreasing graph? And that is because of that reflection over the x-axis. So it went from increasing like this to decreasing, and then shifted right and up. All right, the last thing we're going to be doing today is writing transformations of graphs. So let's look at this example. It says, let the graph of g of x be a reflection over the x-axis followed by a translation 4 units right from this graph, f of x equals 2 to the power of x. And then we're going to create that function. So now you'll see here that we actually have 2 rounds of transformations. So when I do my reflection over the x-axis, I'm going to start with just general transformation form. I'm not going to call it g of x yet. I'm going to start by calling it h of x. So if I want to start with f of x and reflect it over the x-axis, I know that I would multiply the entire function by -1. So that means that h of x, again, I'm just taking this function and I'm putting a negative out front. So this would be my reflection over the x-axis. Now, once we've completed that, they want us to take this and then translate it 4 units right. And so this we can call g of x because this will be our final step. So g of x is going to be h of, and since it's a horizontal translation, we are going to be adding or subtracting to x. So if I want to move to the right, I'm actually going to do x minus 4. So that's telling us to look at the previous step and replace x with x minus 4. So that means that g of x is negative 2 to the power of x minus 4. And there you go. So it is important that we take these problems in 2 steps. Sometimes you could do it all at once and still end up with the same answer, kind of by luck, but sometimes you won't. So again, we're going to break it up anytime we see that followed by. All right, let's do this last example together. So this says, let the graph of g of x be a translation 2 units up, followed by a vertical stretch by a factor of 2 of this function, f of x equals log base 1/3 of x. So let's start with that first transformation. Again, I'm going to call it h of x because it's an intermediate step. If I want to do a translation 2 units up, I would simply add 2 to the entire function. So h of x would be log base 1/3 of x, and then outside of that, plus 2. And this is our translation 2 units up. Now from there, we're going to take that and we're going to vertically stretch it by a factor of 2. So if you are vertically stretching something, you multiply the entire function by 2. Okay? So when I go to do this, I'm going to do 2, and then in brackets, I'm going to write the entire function. I think these vertical stretches oftentimes cause issues for people because it'd be very common to go and just put a 2 in front here and forget to multiply this by 2. You have to multiply the entire function, which means you need to multiply both parts. So our final result is 2 times log base 1/3 of x plus 4. Again, this would be the number to watch out for where I see the most mistakes with these types of problems. So just be careful. If you start with this general function form, hopefully it will remind you that you're simply plugging stuff in. I'm doing 2 times all of this. So it can hopefully help you avoid those small mistakes. Again, that's the vertical stretch by 2. All right, go ahead and pause the video for this last you try. All right, go ahead and check your work here. So first, you take f of x and you subtract 4 from the entire function to do your translation down 4. And then for your vertical shrink by a factor of 1/2, you multiply the entire function by 1/2, which means the 3 to the power of x and the negative 4. So here, just remember, I cannot multiply the 3 and the 1/2. We should not write this as 3/2 to the power of x because 1/2 is not being raised to the power of x. That's order of operations. So we will write our final answer like this. It's 1/2 times 3 to the power of x minus 2. So please don't forget, for vertical stretches and shrinks, you should be multiplying every single part of your function. All right, that's all for today's video. Thank you so much for watching.